All right. Welcome, everyone, to Class 6. Hopefully, you guys had time to absorb the double slit experiment. For those of you that didn't see it, we're going to do an overview of it, But we're going to go over it again in a different way today. So the title of this class is called Entanglement. How many of you heard of quantum entanglement? Yeah, a lot of people heard of it, but we're actually going to break down what it is, So Richard Freeman, who's a famous, he's probably like my favorite physicist. And the reason why is he's one of the few geniuses, and he's high level genius. Not quite Einstein level, but as high as you can go, whatever. Huge contributions. But he actually had the gift of teaching. Yeah, all these guys, like Einstein, nobody understood what Einstein's theories meant unless you were like super smart, It took other geniuses to break it down in layman's terms, So Richard Freeman, you can actually watch him. They just released his lectures for free. I encourage you if you're interested, And he does them like, the original ones were like back in the 50s, and they're like black and white, And then in the 60s, and he does them in like later in the 80s and 90s, But here's a quote that he said that I really like. He said, "The two-slit experiment contains the only mystery. We cannot make the mystery go away by explaining how it works. In telling you how it works, we have told you about the basic peculiarities of all quantum mechanics." So that experiment we went over at the end of last class, there's no real explaining it. Like I explained it, but you see all it does is open up more questions. And we're going to kind of go over that. So the first thing we're going to go over is we're going to go over another version of it. It's called the box pairs version. So this time, instead of going through slits, we're going to fire a particle at a silvered mirror, where half the light goes through, half reflects. Of course, as soon as we fire a particle, it turns into a wave, whatever that wave is. And half the wave will go through, and half the wave will bounce off. And this top one is a mirror. It's just going to bounce off the mirror, and we're going to catch them in a box. So as soon as they go in the box, we're going to close the boxes, and they're just going to bounce around. We're not going to really know what they're doing. The mirror splits the particle's wave function into two discrete packets. Both are routed and captured in two separate boxes. The wave function will simply bounce back and forth in the box until it's observed. Why do I even talk? I hate it. Dividing the wave function of a particle into well-separated regions is accomplished in every actual interference experiment with atoms. So this is exactly what we did in the double slit, because it went through the slit, turned into two packets, two waves, that then interfered with themselves, and yada, yada, yada. So here's a blow-up of that, just in case you can't see it. All right, so if you open both boxes, so imagine these boxes, imagine there's these box pairs. And first imagine that we do this, let's say we have a stack of 1,000 boxes, right? And each of us does 100. And every time you do it, you have, you just take them and you capture them. And you just take those boxes and you put them aside and do another pair of boxes. So we have a whole bunch of boxes, all with bouncing atoms inside, right? Now, these boxes have imagine like a little trap door that opens up. Or a better way is imagine they have a little button that you press, so that way they both open at the same time. So if we were to open them both at the same time, as you can imagine, both the wave packets would go out, and we'd have a screen to capture them, and we would get an interference pattern, right? Because if we open both boxes at the same time, we don't know which box the atom was in. And if we don't know, then we get an interference pattern, remember? It's the fact of observing, it's the fact of knowing which slit it goes through that collapses the wave. So open one box at a time and the interference pattern will disappear. So if we open just one box and then another box, then there is no interference pattern. Why? Because if we open a box and then on our little computer screen we see a dot, then we know the atom was in that box. It's the same thing as saying I know which slit it went through. So the common terminology they use is they call it the which path information. Because in all these experiments, there's always multiple paths, whether 2 slits, 3 slits, 4 slits, 5 slits, 100 slits. So if you know which path it took, then you will get the clump pattern, like the 2 lines, if you remember, because you know where it went. If you're not looking and you don't know the which path information, then you get the interference. Remember, the waves interfere with each other. So what explains a whole atom appearing on a screen when some of it had come from each box of its pair? So if now let's go backwards a little bit, and we're going to try to break this down logically. So there's a little bit of each atom in each box, right? We open them both up, and what hits the screen? Just one atom. So if there's a little bit of an atom in each box, and this is what we're thinking logically, how does one atom appear? Might it also make sense to say that part of each atom was in each box? In that case, part of the atom emerged from each box and then congealed on the spot on the screen where you found it. So if we're taking these waves literally again, which we shouldn't, we've already established that, but we have sort of atom, part of atom in each box. If when we let them go and one atom appears, those two waves had to mesh together to form an atom. This is reasonable sounding idea, so why doesn't it work? Which we know why, but we're going to just go through some logic for logic's sake. So opening one box slit, you will sometimes find one whole atom hitting the screen. So when you open the second box, nothing will come out and vice versa. So if you look inside a box and nothing comes out, then you know the atom's in the other box. Because in each pair, there's always one atom. In other words, you get a clump pattern. A clump pattern is when you just get the two slits of particles. Repeatedly opening the box pairs in this fashion, you determine which atom was in which box. So if we open one at a time, we always know which atom was in the box, right? So if I open a box, nothing registers, it's in this box. And if I open it and the atom hits the screen, then I know, it was in this box. So we have two different experiments. One in which we open one at a time and we always know which box it's in, or one in which we open them both at the same time and the atom hits the screen, but we see the interference pattern. So we have this whole, it came out of both boxes. You demonstrate that there had been a whole atom in one box and nothing in the other box. There's a more direct way to establish that one box contained either one whole atom or nothing at all, is we look. Now we don't have to open slits, we can just look. If we were to look inside this box, now of course we're talking about an atom, so we'd have to use some type of measuring device. But as soon as we measure it, what happens? It collapses and we're not going to see interference. So of course, it doesn't matter how you look. About half the time you'll find an atom in the box, and the other half the time you won't, because it's 50-50. Really simple probability. If you found one box to be empty, then there will always be an atom in the other box. All right, so again, we established that each atom was concentrated in one box of the pair, and it wasn't spread out over both. But before you looked, you could have done an interference experiment, establishing that some of each atom was in both boxes. You therefore could prove either that the atom had been wholly in a single box, or you could choose to prove that the atom was not wholly in a single box. Does this make sense? Exactly. So again, I grab a box pair. If I open just one, what am I doing? I'm going to establish it was in this box, or it's not in this box, it's in this box. I established that there was an atom in one of the boxes. If I grab another box pair and I open both the slits, I established that the atom, because of the interference pattern, the atom had been in both boxes. Two totally different contradictory things. You can choose to prove either of two contradictory situations. So the ability to prove either situation is the puzzle. This is at the heart of everything quantum. So what if you do experiments with the same pair of box? So what if we open the box pairs at the same time in order to get an interference pattern, but then you also look to see which box the atom came out of? What would happen? It would collapse, just like the slits. You know, the slits, it was interference, but as soon as we looked to see which slit it came out of, it collapsed. So it's the exact same thing. It's just now we're doing boxes instead of slits. Well, you should all know the results of the experiment since it's the same as the double slit experiment. Absolutely anything you do that would allow you to know which atom the box was in will give you a clump pattern. When I say clump, in these boxes they go in clumps, not lines, because they're not slits. But seeking a loophole, a lawyer might establish that the interference experiment relies on circumstantial evidence. It uses one fact, the interference pattern, to establish another fact, that one atom came out of both boxes. So legally, this is all circumstantial. Like, we can't prove It's impossible to prove that the atom was in both boxes. Because as soon as you look, you see one atom. The only way we know is that when the atom appears, and we do thousands of them, they go in exactly the places where waves would. So circumstantially, we know it's because of waves. But it's not direct proof. This is true of any interference experiment. Finding no other reasonable explanation, physics readily accepts interference as establishing spread out waviness. As in our legal system, circumstantial evidence can establish a conclusion beyond a reasonable doubt. So if you are caught, your wife is dead, you have a gun in your hand, you have gunshot residue on your arm, you have her blood on you, we didn't see you murder her. It's all very circumstantial, But it's very, very good circumstantial evidence, And then there's we all know the weak circumstantial evidence, But regardless, it's all circumstantial, unless you got it on tape. And nowadays, James Cameron and Weta Workshop, they can digitally have you kill someone. Ain't nobody know the difference. So any theory leading to a logical contradiction is an incorrect theory. That's just common sense. So if that's true, then does the ability to demonstrate either of two contradictory things about atoms invalidate quantum theory? Yes or no? Nenny? The answer is no, of course. But why? Well, because we did not demonstrate the contradiction with exactly the same thing. I didn't show you that the atom was wholly in a box and then use that same box pair to then show you it was in both boxes. Because the box pair was over. I had to grab a new set of boxes. So there is no contradiction per se. We did two experiments with two different sets of boxes of atoms. So let me propose another logical explanation of our ability to prove two different things in two different sets of boxes. Those box pairs that we demonstrated the interference pattern actually contained objects spread out over both boxes, not wholly in a single box. So I grab a pair of boxes, and I open them both up, and I get an interference pattern. Logically, you would have to come to the conclusion that there was not an atom in each box, and that it was spread out between both boxes. Contrastly, if we take a box pair and we did the which box experiment, you would have to propose logically that those boxes didn't have a spread out atom. There was actually one atom in one box and nothing in the other box. That's why you got both. Makes sense, right? How could we establish otherwise? That's the only logical explanation for this. Of course, we reject this. Now, why do we reject this explanation? John? No, we reject it because we chose the boxes. So if the only logical explanation is that this box pair actually has one atom in one box and one atom in the other box, and I grab it, but I make the choice. I decide right now what I'm going to do. I could decide to open them both, or I can decide to just open one. So we have to reject this because we know that given a pair of boxes, we could have made either choice. We chose freely which experiment to do. Did we want to know which box, or did we want to know not which box? We have free will. Last time I checked. So does our free will determine the external physical situation? So does the fact that I choose to do something, like I choose to open both the slits, does that then determine what's going to come out of the boxes? Or does the external physical situation predetermine your choice? So do I not have free choice? I may think I'm choosing to do the which box experiment, but in reality I'm not choosing because it's already been determined. This should all just mess with your head. I'm just saying.
But don't you got a free choice to do that?
Well, yeah. Well, are you making a choice? Like if you're making a choice to know which box it's in. How is that different from the fact that there was an atom in one of the boxes, because it's true, and that actually determined your choice? It goes both ways. Either way, it doesn't make any sense. So, yes.
Possible that the one that has the atom in it, if you open that, and does it use a wave particle dance thing?
If you open one? Yeah, no, if you open one, that's when you get the two lines. So it acts just like if you were just to let go of a particle, just like Newton. Now remember, we can't see waves. All we can see is a circumstantial evidence of a wave, you know? We're just doing the double slit experiment, but with boxes. That's all you missed so far.
Okay, I have a question for you.
Yes?
How did you open both boxes with no atom?
Well, that's the one condition, is each box pair we do have either one whole atom in a box and nothing in another box, or we have a spread out atom within both boxes. So we experience, the whole enigma is experienced only because we believe that we could have done something other than what we actually did. That's the premise. Free will. So we reject that because we're like, no, but I could have, I opened both, right? And it's spread out. But I also say like, well, I could have just opened one. I made the choice at that second which thing I wanted to do. And depending on what you do, that's what happens. So did what happens happen because you chose it, or did what you choose because it happened? It's whatever. So the denial of this freedom of choice requires our behavior to be programmed to correlate with the world external to our bodies. This puzzle arises from our conscious perception of free will. So the whole puzzle is contingent on the fact that we know we have free will, at least we think we do, at least we believe we do, and the fact that how does what I do affect something else? You know? Our present actions obviously determine the future, right? So if I drop my phone, it will fall. All right, we know present goes to the future. But obviously our present actions can't determine the past, right? So logically, if we have free will, right, then it would make sense that finding an atom in a single box means the whole atom came to that particular location, came to that particular box on a particular single path after its earlier encounter with the semi-transparent mirror. So choosing an interference pattern would establish a different history, that aspects of the atom came on two paths to both boxes after its encounter with the mirror. So here's a possible explanation. This is what we talked about before. Isn't so much a violation of free will. It isn't so much that it's trying to change you, but it's possible that what you do in the present actually changes the past. So let's say when I did that experiment, the atom actually went into one of the boxes. All right, and I grabbed that pair. And now I open both of them. So my choice to show that if I open both of them, I'm trying to show that it's in both boxes, not one of the boxes. So I've literally made a choice now, and I've gone back and rewritten its history. So back when the atom went in the boxes, instead of just bouncing off the mirror and going in one box, the atom split and went in both boxes. So it just happened that it's doing what I chose it to do. So now we're saying, okay, I have free will, but whatever I will not only happens in the future, but it actually changes the past to match the future, which is bizarre. So the creation of past history is even more counterintuitive than the creation of the present situation. So it's bad enough saying what you do now changes what happens, but now we're talking about what you do now change the past so that it also happens to what you're doing. Nevertheless, that's what this experiment shows us. So that's how we can interpret it. Or we can interpret it those other bizarre ways. Either way, you have a really bizarre picture of the world. Quantum theory has any observation creating its relevant history. So quantum theory in the mathematics, it shows you possibly, we're going to actually debate this later, that you're actually going backwards and changing what happened to match the choice that you made. So in the box pairs experiments, I described only what you would actually see. Remember, this whole time, originally I was talking about quantum theory. Remember in the first class I tricked y'all, you know, or I was like, oh, theories and all. I'm not even talking about theory. This is what happens. This is just experiments. Now, quantum theory actually explains it mathematically. Quantum theory was never mentioned this whole time. I'm just telling you what happens. The quantum puzzle exists independently of quantum theory. Now, this is important because whether it's evolution or this and that, or it's the Big Bang theory or superstring, it's like there you have the theory trying to tell you what may happen. Like, no, this is what happens. And the theory explains what actually happens. Quantum theory provides a mathematical description that correctly predicts the results of the experiment, of the observations we choose to make. So, now that we've established the experimental basis of the phenomena, what is quantum theory's explanation of all this? We've gone through our explanation. What does the mathematics actually tell us? Since we can choose an atom to be either of two contradictory situations, how does quantum theory describe the state of an atom before we observe it? Quantum theory describes the world in mathematical terms. So mathematically, the wave function, and this is a translation, I'm not going to start throwing equations at you, but basically the wave function is the atom is wholly in the left box. That's direct translation. And for the other box, the wave function is the atom is wholly in the right box. So the unobserved atom mathematically is written as the atom is wholly in the left box plus the atom is wholly in the right box. So the atom is said to be in superposition of these two states. And it was mentioned in the video, probably didn't know what they were talking about, but that's what you hear about all the time. Quantum, I always say quantum supposition when you say it fast, but it's quantum superposition. So it's not just that you have a position, you got a superposition, because you're in two places at once. That's pretty super. It is simultaneously in both boxes, or in both states. On looking in a box, this sum, or superposition, collapses randomly to one or the other term of the superposition. So before you look at it, it's this plus this. As soon as you look at it, it randomly will become one or the other. The other term will drop. So before we look, mathematically, the atom is simultaneously in both boxes. The atom is in two places at once. So observation collapses the waviness, the probability, to a specific actuality. So now, again, the question posed is, what constitutes observation? What is observation? Yeah. Like, if my dog looks at it, like, does it collapse? Well, how would you know? Is it the dog? We taught the dog to talk, like, up. And the dog says, yes. Then does it collapse as soon as you heard it say yes? Because now you consciously know? Where does the collapse happen? The Copenhagen interpretation of quantum mechanics defines observation as any recording of a microscopic event by a macroscopic recording device. So everyone knows what microscopic is. That's all the stuff you can't see. Macroscopic is the opposite. It's all the stuff you can see. So the Copenhagen interpretation, which is the predominant interpretation that physics use to make sense of all this, says that observation is when you look at the microscopic with something that's big. Obviously a measuring device, a laser, telescope, something. So how does nature decide on a particular result or a particular box when quantum theory, our most basic description of nature, gives only probability? Now here's the key, and this is where you can easily throw off all the New Agers. Because remember I told you there's a lot of New Age nonsense like create your reality. You know, Neo in the Matrix, you know, like what does he do? He can stop bullets. Like he can consciously like change reality. Well, that never works. And this is why, and I've said it 100 times, but maybe it's more clear if you just state it directly, is that there is an intrinsic randomness associated with the observation. So choosing to observe an atom wholly in a single box, we can't choose in which box it will appear. It's completely random. We can't choose it's going to be in this box. No. All we do when we observe is we determine one or the other. Completely random. And they've done a billion experiments to try to find patterns in the randomness or whatever. And I don't know if you remember, I think I said in class 2 that doesn't work. Actually, true randomness can only be generated from watching quantum, watching atoms shoot stuff off in totally random patterns. So on choosing in an interference experiment, we cannot choose in which of the allowed regions the atoms will appear. We can choose the game, but not the particular outcome. So just this simple fact that now should make sense because we've gone slowly into it invalidates 90% of what you will find on Amazon.com. If you type in quantum. Yeah. Wave functions collapse with randomness. All right? Said it 100 different ways. Just want everyone to know. So Lucy, all that, never happens, you know, because the premise of the movie Lucy is exactly what the New Agers say, is that once you tap into this quantumness and you're using your whole brain, which is garbage, we're using 100% of our brain. We're only using 10%. Anyways, but it's just like once you tap into that, then you could be like God because now you can consciously change everything. No, all you can do is do what we do. We can consciously have something randomly happen, and that's sort of the name of the game. So let's go more into depth in this Copenhagen interpretation because it's pretty crazy. So the Copenhagen interpretation rests on three basic ideas. The probability interpretation of the wave function. We talked about that a lot. Remember about probability. It's not a probability like it's under a shell. It's a probability that it will even exist. It's not actually there. Then there's a Heisenberg uncertainty principle, which we talked about a lot. And then there's the principle of complementarity. I just can't say it. Complementarity. There we go. Okay. I'll pronounce it in my head. So quantum probability is not the probability of where the atom is. We've already gone over this. It is the objective probability of where you or anybody will find the atom. The atom wasn't someplace until it was observed to be there. Since quantum theory has no atom in addition to the wave function of the atom, if the atom's wave function occupies both boxes, the atom itself is simultaneously in both boxes. Its later observation causes it to be wholly in a single box or not be in the box. So what constitutes observation? We'll go over it again. So here, for a photon bouncing off an atom, there's a clear answer. The photon does not observe the atom. So if we're going to try to look like, remember it's going through the double slits. How do we observe it? With a laser or something. So we shoot a photon. All right, it bounces off the particle. Does the microscopic object observe the microscopic object? Like we can't see our red blood cells. Red blood cells are hitting other red blood cells. So do other red blood cells see red blood cells? The answer is no. After the encounter, the photon and the atom are together in a superposition state. That includes all possible positions of the photon and the atom. This can be confirmed via experiment. So on the other hand, if the photon bounces off the electron and then hits a detector, that's something now we can read. Then what have we done? We've observed the microscopic with a macroscopic, something that we can see. The computer screen tells us, hey, I just registered something. That's what an observation is. That's what constitutes observation. Now, it still doesn't solve any of those problems that we went over in Class 1, but we'll see how they deal with that. So what about being unobserved? Consider the atom in our box pair. Until the position of the atom in a particular box is observed, the atom doesn't exist in a particular box. And remember what we talked about before, I hope to prove at the end of last class with the very last version. Remember where we let the wave go through both slits? Yeah. And then we had the film, and then we pull the film away, and the wave's already going through, and then the wave disappears. The whole point of that wasn't just to show retrocausality, but was to show that these aren't really waves. Now, they behave like waves, but they're not. Don't even think in your brain like they're waves of something, because they're waves of nothing. They're a wave of a probability that it will be there. I know it's weird, but we nevertheless initially observed the atom when we grabbed it and sent it into the box pair. The atom's position in the pair of boxes is thus an observed reality. However, taking the extreme of a very large box, we can say the atom essentially has no position at all. It does not have the property of position. The same can be said of any unobserved property of an object. This all goes back to the Heisenberg uncertainty principle. The Copenhagen interpretation generally adopts the view that only observed particles of microscopic objects exist. Now, John Wheeler, we'll hear about him more later. He's another really famous physicist. He said this: no microscopic property is a property until it's observed. So, if we carry this to its logical conclusion, microscopic objects themselves are not real things. Okay, now we're going to run into trouble. This is what Heisenberg said. In the experiments about atomic events, we have to do with things and facts, the phenomena that are just as real as any phenomena in daily life. But the atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. Remember, and Heisenberg was just looking at just the mathematical sense. He wasn't trying to be philosophical about it. So according to this view, atomic scale objects only exist in some abstract realm, not the real world. So since they only exist in an abstract realm, it's okay if they don't make sense, you know. Now remember, I don't know if I mentioned it last class, but the way it's written, it's called this abstract world. We can model it mathematically. It's called a configuration space, and for every particle, you need to represent that in 3 dimensions, in a 3-dimensional configuration space. But when I say, it's not like every particle needs its own 3 dimensions. So if you have 2 particles, then you're 6 dimensions. 3 particles, 9 dimensions. Now, when I say particles, I'm talking about the smallest pieces of atoms. So just a tiny, tiny speck of dust, which is 1 trillion atoms, is a 1 trillion-dimensional configuration mathematical space. Now, we can model that and use computers to come up with stuff, but it's way beyond even, anything you want to try to even think about. So if the microscopic world consists merely of possibilities, how does physics account for the small things that the big things are made of? This all goes back to class 1. If nothing is real that we can't see, but everything we can see is made up of little things, how do you deal with that? Well, this is what the great Niels Bohr said. There is no quantum world. There is only an abstract quantum description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns with what we can say about nature. So he just danced around the whole issue. He's like, look, physics all we're trying to do is explain how nature is. We're not trying to explain nature, which drove Einstein mad. The Copenhagen interpretation avoids involving physics with consciousness by redefining what has been the goal of science since ancient Greece, to explain the actual world. And the last is complementarity. Complementary. Let's say complementary. The 2 aspects of a microscopic object, its wave aspect and particle aspects, are complementary. And the easiest way I describe this is it's yin and yang. So if you have the position, then you have no momentum. If you know its momentum, then you have no position. You can't have one without the other because they're yin and yang. They're complementary. So a complete description requires both contradictory aspects, but we must only consider one aspect at a time by specifying the kind of observation we're making or the experiment we are doing. Bohr states that physicists talk of atoms and other microscopic objects as if they were actual physical things. Microscopic objects are only concepts we use to describe the behavior of our measuring instruments. Now this is just, it sounds absurd, but he's like, if you can never see the small, and everything you see in the small is a direct reflection of what you're measuring it with, then he's saying the whole point of microscopic things is just to describe the behavior of the big things that we're using to use of the microscopic things. I know. We need to go beyond describing the behavior and dealing with the microscopic world. Oh no, he said we need not go beyond describing the behavior and dealing with the microscopic world. So basically it's a big cop-out. They're like, you know what? We don't worry about it because we can't see small things. So you don't have to worry about the fact that the small things aren't real. Because if we try to look at the small things, we know they don't exist. They're not really real. But we know the big things are real. So for all intents and purposes, don't worry about the small things. In addition, the Copenhagen interpretation states to not think about experiments that you might have done but did not in fact do. So after all, it was just the perception that we could have chosen to do an experiment other than the one we actually did that gave rise to the quantum measurement problem. Remember, the whole problem, free will and all this, is the fact that we could have chose what to do, right? He's like, no, don't. You can't think about experiments you didn't do or that you could have chosen to do. One eminent physicist proclaimed, not done experiments have no results. Since physics is just about experimental results, we need not even think about the not done experiments. And what Galileo said, the whole goal of science is to prove what you can do by experiment. And that's what quantum physics does. Of course, we now are going beyond that. We're like, but what if I chose a different experiment? Well, what if, could have, should have? You didn't.
Yeah.
I can't give you results on the experiment that you may have chosen you could have done. Our usual assumption that we could have done other than what we actually did is called counterfactual definiteness, which I usually say counterfactual definitiveness. And this we're going to hear more. But that, if I say counterfactual definitiveness, that's what it means. Is that if I drop this and let it go and turn around, I assume that it fell. Why? Because things always fall. The quantum world, no. As soon as you let it go, you don't know what happened. The fact that you assume that it fell, that is the fact that you think you know what it's going to do based on past experiments. But did you do the experiment? The experiment means, did you watch it fall? No. If I don't watch my phone fall, it didn't fall. So it's counterfactual definitiveness. Believing that if you did not eat lunch, you'd be hungry assumes counterfactual definitiveness. You don't know that if you didn't skip lunch, you're going to be hungry. Sometimes I go the whole workday and I didn't even know I didn't eat lunch. So quantum mechanics denies counterfactual definitiveness. This would seem to defy free will. A simple interpretation of Copenhagen is shut up and calculate. It's like, why worry about it? You know, if you're a student, we've all been in school. Look, you're not trying to get all deep thoughts with Jack Handy on this. Like, you just want to get an A on the test. You want to get out in time to hang out with your friends. You want to get you want to get a good score on your homework. You just want to calculate. That's all you do is calculate. So don't worry about it. Copenhagen assures us that in our labs and at our desks, we can use quantum mechanics without worrying about what's going on. Don't worry about it. Schrödinger was horrified at this, obviously. Using reductio ad absurdum, which is a classic philosophy logic thing, which means reduction to absurdity, Schrödinger told a story to argue that quantum theory led to absurdity. So Schrödinger was already pissed because the whole reason why he got into this was to stop jumping, remember? Turns out he didn't stop jumping. He was like, oh, why did I get involved with this? And then as a couple of years went by and Bohr started coming out with this stuff, he was like, this is ridiculous. So he actually used the box experiment to then come up with the cat story. So remember the original experiment, there was a little radiation detector, right? And if a little bit of radiation hit it, it dropped the hammer, which then opened he didn't crash it. It pulled the stopper out of the vial of cyanide, which then killed the cat. Now, imagine that atom is a radioactive atom. Well, according to this, it's in both boxes. So it opened up the cyanide and killed the cat, and it didn't kill the cat. Schrödinger was like, if you set up this experiment, and if what you say is true, then that means the cat is alive and dead at the same time. Now remember, he wasn't doing this to boast about quantum mechanics. He was trying to say, look, you can't have an alive and dead cat. It's impossible. But with this microscopic object, like maybe you could. How would you know the cat's alive or dead? Assuming it wasn't scratching or blah, 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 or making any movement, you know. Here's a famous quote by Stephen Hawking, which I love. When I hear about Schrödinger's cat, I reach for my gun. That's kind of like the universal consensus, you know. And there's another Schrödinger's dog. Shh. Put the cat in the box with the poison gas to demonstrate the influence of observing quantum mechanics. I thought that was funny. All right. So scientists have created macroscopic objects in quantum superposition. Now listen to what I just said. They do experiments to test this, right? And as they get better and better at this, I think about 10 years ago, they did it with like a buckyball. It was a huge big deal. A buckyball is like 280 atoms in like a really cool configuration space. So now they're not just able to show that electrons are here and there, and not just that a whole atom, which is a whole bunch of electrons, protons, and neutrons, but they were able to show that whole groups of atoms. They've actually created, and I think it was in 2004, and I had a picture of it, but I didn't put it in here. It's hard to see. They made a macroscopic object in quantum superposition. So macroscopic is something you can see. All right? So made up of over 1 trillion atoms, it was a macroscopic hammer. It was a little hammer. And it was visible to the naked eye. Now, when I say visible to the naked eye, it was like a fleck of dust. I mean, you really needed a low-powered microscope, a magnifying glass, to get a good look at it. But if you did look closely at it, you could see the hammer vibrating to and fro, and at the same time, it wasn't moving. It was like alive and dead. It was vibrating, but at the same time, it wasn't moving. So you were actually seeing, this is the closest thing you can get to seeing something be here and there, on and off, alive and dead. Now the weird thing is you look at it, it just looks like a hologram. You know, like imagine that fan, and imagine I photoshopped the blade not moving, like on top of it. You would think like it's like, oh, it's okay. We all know what a spinning fan looks like, and we all know what a blade of a fan looks like when it's not moving. You see them at the same time, and your brain's just like, okay, is it behind it? No, what you're at. If I were to tell you, like, actually, no, you're seeing the blade spin around and not spin around. So just the fact that you see it still doesn't help. But the fact is, this is real. It's so real that they're actually able to make it macroscopically, which is a huge achievement. Even though it's a speck of dust, we're talking about trillions and trillions of atoms. Albert Einstein says, I think that a particle must have a separate reality independent of the measurements. That is, an electron has momentum, location, and so forth, even when it's not being measured. I like to think that the moon is there even when I'm not looking at it. So Einstein comes in, all right, and Einstein thought this was all rubbish. Thank God. So the Copenhagen interpretation, although it tried to be subtle, is not denying a physically real world. The fact that it claims that objects of the microscopic realm lacked reality before they observed was even more absurd to Einstein than it was to Schrödinger. Einstein championed science's role in explaining how nature worked, which is what we think all scientists would want to know, is like explain how things work. But quantum's like, we're just saying what happens. Bohr's statement that science's role was only to explain what we could say about nature infuriated Einstein. He insisted that even little things have a reality regardless of someone is looking at them or not. If quantum theory said otherwise, it had to be wrong. So that's what he wanted to show. Is Bohr, you are wrong. Niels Bohr, the Copenhagen architect, rose to its defense, and for the rest of their lives, Bohr and Einstein debated as friendly adversaries. I say friendly, it's like, you know, they weren't haters, they weren't like rivals, like, you know, like they came together and spent like, you know, vacation together, so to speak, like in the classroom for weeks on end and debated these things. So to argue quantum theory was inconsistent and therefore wrong, Einstein would attempt to show that even though an atom participated in an interference pattern, it actually came through one slit. So when we see an interference pattern, we do by circumstantially, we say, oh, then it's a wave, and it really came through both slits. Einstein's like, no. If we can prove that even though it behaved like a wave, but it really only came through one slit, then we can start invalidating the stuff. So to demonstrate this, he would need to invade the Heisenberg uncertainty principle. And ironically, Heisenberg attributed the idea of the Heisenberg uncertainty principle to a conversation he had with Einstein. That's just one of those funny things. All these guys talk to each other. At the Solvay conference, and I didn't really go over this, I wanted to show a picture. The Solvay conference, they had it every 3 years, is when all these dudes would come together. Like, it was like the genius get-together. They'd all discuss the new ideas and this and that, and it's cool to see these pictures, especially when you start seeing know all these guys' faces, and you see all these geniuses all just side by side, in like class photo. Bohr readily pointed out the flaw in Einstein's reasoning. Oh, sorry, I skipped. So at this conference, right, Einstein challenged Bohr with a thought experiment devised to derail quantum mechanics. I won't go into what it is because it was just kind of simple. The whole point is Einstein, remember, he's the man. Bohr's still kind of up and coming, but he's the rising star. So Einstein challenges him in front of all the world geniuses, everyone at the top of their game. And Bohr, it wasn't that he just, let me think about it, like he readily dismissed it using simple algebra, and he was able to show how Einstein's thought, Einstein's attempt at making fun of Bohr, saying, this quantum theory is not all it's chalked up to be, was false. So it was a little embarrassing for Einstein, but not really that big a deal. 3 years later, at another conference, Einstein proposed another experiment claiming to violate the uncertainty principle. So this is the next time they come together. Once again, Einstein's trying to come at Bohr. So now it's not just a matter of fact. Now it's like Einstein's really thinking about this. This time, Bohr was stumped through one long sleepless night. But in the morning, he embarrassed Einstein again by showing that he had ignored his own theory of relativity. So Einstein comes at Bohr, and Bohr's he's stumped, and he goes all night, barely gets any rest, but after he wakes up the next day, he said he had a revelation. And the next day he comes there, and Einstein's probably all proud of himself, like, this young buck, And he ends up disproving Einstein because Einstein had ignored the implication of his own theory. So this was really embarrassing. And it's embarrassing for Einstein, not that people would think Einstein's any less, but it was really a big boost for Bohr. Like if you're an up-and-coming young physicist and you outthink the great thinker, it's good for you. So Einstein again was embarrassed, but was convinced that the theory was at least consistent and that his predictions would always be correct. So throughout all this, Einstein, he came a little bit over. He's like, okay, look, I get the theory is consistent. It works. You get correct results. But I still think you're missing something. So a humbled Einstein went home to concentrate on general relativity, which is his theory of gravity. That's his final triumph. Or so Bohr thought. Now, we don't know what Einstein was doing, but he knows he wasn't just working on relativity. Because the bolt out of the blue, Bohr was wrong. Einstein had not abandoned his attempt to fault quantum theory. 4 years later, so 4 years after he got embarrassed, out of nowhere, in 1935, a paper, he mailed the paper to him. This time he just mailed it to him. Written by Einstein and two young colleagues, Boris Podolsky and Nathan Rosen, arrived in Copenhagen. An associate of Bohr was quoted as saying, this is one of Bohr's minions, "This onslaught came down upon us like a bolt from the blue. Its effect on Bohr was remarkable. As soon as Bohr heard my report of Einstein's argument, everything else was abandoned." So Einstein, again, produced a case, and Bohr's like, whoa, 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 whoa. Everyone, stop what you're working on. Like, we need to respond to this, And they did. It took about a whole month to come up with a response. The paper, now famously referred to as EPR, for Einstein, Podolsky, Rosenberg, did not claim quantum theory was wrong, just that it was incomplete. EPR argued that quantum theory did not describe a physically real world. It required an observer-created reality only because it was not the whole story. So everything we've been talking about, Einstein's like, it's just an illusion. It only seems that way because you're missing something. EPR showed that you could, in fact, know a property of an object without ever observing it. That property, EPR argued, was therefore not observer-created. Not being observer-created, it was a physical reality. And if quantum theory did not include such physical realities, it was an incomplete theory. Now, I went over it really fast at the end of this class, but we'll go over it again. But first, we'll go over real quick polarized light. How many of you guys have heard of polarizers? Polarized? You may not know what it is, but So instead of mulling over Einstein's thought experiment, let's review the real one. So Einstein's experiment involved two trains, spring, blah, blah, blah. We're going to skip that, and we'll maybe talk about it later. But we're going to go over the actual experiment that proves it. So to do that, we need to go over what polarized light is. So first, we have to remember that we all know these are waves. But we forget these are just two-dimensional waves we write on paper. Real waves are three-dimensional.
Yeah.
All right? This is the electromagnetic wave. So in every wave of light, you know, the electrical wave is offset by 90 degrees perpendicular to the magnetic wave. That's why they're always together. But the fact is they're three-dimensional. All right, don't get two-dimensional. And then here I found this really cheesy video which sort of sums it up. Polarizers.
Ordinary light rays oscillate in different planar orientations. Light rays vibrating in different orientations approach this polarizing glass filter. All light rays with an exactly vertical orientation pass through. Light rays with an exactly horizontal orientation are blocked. Most light rays have orientations that are partially horizontal and partially vertical. The amount of the ray that passes through the filter is proportionate to its verticality. The rays that pass through are polarized to be completely vertical.
All right, so a polarizer, you think of it as has really, really, really fine slits, okay? Light, like from flashlights, those waves, three-dimensional waves, are coming in every single angle. So from, 90 all the way to 180, I mean, however you want to do it. So when it hits a vertical slice, all the light is going to come through vertical, right? If it's exactly vertical, it's going to come through 100% vertical. The more it tilts, it's going to still come through vertical, but it's going to be dimmer and dimmer. And eventually, when you get to horizontal, it's blocked completely. Does that all make sense to everybody? Oh, and here's an actual example. This guy's showing, because this is the basis of all our technology, except for organic LEDs. So every single LCD, every single screen you look at on every computer and every TV, except for a Galaxy S3, S4, and Note, uses polarizers. And it means this. So here he has a sheet. You see, as he turns it, oh, it blocks all the light. He turns it back, and it's clear. Blocking the light, coming clear. And then he actually grabs another one, and you can do cool things where you put one in front of it, and depending on how you can let light through when it's not let through.
Yeah.
And that's the technology that our TVs use to turn it on and off. But you can see these are very simple devices. And if any of you are amateur photographers or cinemas, you have these lens guys, when you go fishing, you put on the polarized lenses and all that glare disappears. Well, why? Because the slits are built to block all light at a certain angle. So light bounces off the water, that glare is all at a certain angle. So the polarizer blocks that whole angle of light. And now the water is just perfectly clean. Because you still have all the other light hitting it, but just not the light bouncing off your eyes. And now you look down and you see the fishies, So you have this thing called a twin state photon. All right, there's a certain type of atom, when excited with a certain energy state, it will emit two photons of energy in opposite directions. So rather than get all worked up of how it works, just know that there's this phenomenon, and the atom gets excited, and it ends up spitting out two photons, all right, with the same exact polarization. That's why they're twin states. Both photons will have the same exact polarization angle, making them twins. So if you measure one light wave to be 45 degrees, so here's the twin state photon, it shoots two out, right? I measure it, it's 45 degrees. Anne's over there. As soon as Anne measures her, it's going to be 45 degrees, because they're twins. They're always going to be the same, all the time. And as you can imagine, this would be very helpful for Einstein's experiment. So here's our atom. I made it 45.6 degrees, whatever. And the classic they always use is Alice and Bob, all right? So Alice is over here, and Bob's over here. Now Alice is going to make a measurement. She's going to move closer, all right? She's going to move closer to where Bob is, and she's going to measure it. So she measures this at 45.6 degrees. Now this is moving at the speed of light, okay? So let's assume they're really far away. So Bob is over here. The wave hasn't reached him yet, right? Now, according to quantum mechanics, what is that wave? It has no angle. It has all angles simultaneously. It's in superposition. But we know as soon as Bob measures it, it's going to be 45.6 degrees. So let's say Bob were to actually get a box, just to be easier, just like our box experiment. And he captures it, bounces back and forth. Anne gives him a call. Oh, Alice. Alice gives him a call and says, "Hey, Bob, you got a photon wave?" He's like, "Yeah." It's like, "I bet you $50 it's 45.6 degrees." Sure enough, he checks. It's 45.6 degrees. So as you can see, we basically invalidated everything we just said, so to speak, because I've been telling you, ooh, it's not really there. It's everywhere, you know? No, this simple experiment, which is relatively simple, we know that it is really real, that these waves really do have a real property, because when 100% of the time, Alice is going to know what angle Bob's light ray is. Make sense? So quantum theory has twin-state photons having identical polarizations, but does not include their particular polarizations as a physically real property. Quantum theory has the polarization as a superposition state of all angles at the same time, and it is only when you observe the light wave that its polarization angle collapses into a definite angle. Again, this is everything what I've been saying. Nevertheless, quantum theory claims to be a complete theory. Now you can understand why Bohr was like freaking out and why he really had to think about it. But Bohr, he freaked out not in the way we would think. It wasn't like he was like, oh my gosh, I'm wrong. It was more like, oh my gosh, I didn't know this is also happening. And what did he see also happening? To dispute, oh, hold on, let's finish the writing. To dispute the claim of completeness, EPR had to say what constituted a physically real property. So again, if Einstein's going to say that real is real or this isn't real, you have to define what is real. Defining reality has long been and still is a philosophical issue. EPR offered a minimum condition for something to be physically real. So EPR then argued that if such a physical reality existed and was not described by quantum theory, then the theory was incomplete. In other words, if a physical property of an object can be known without its being observed, then that property could not have been created by observation. If such a property were not created by its observation, it must have existed as a physical reality before its observation. Quantum theory does not contain any physical properties that are real in this sense. Quantum theory says, no, nothing's real until you look. When he received the paper, almost a decade after the Copenhagen interpretation was developed, Bohr had not yet realized the implications of quantum theory to which EPR objected. So again, Bohr, instead of freaking out, he got excited because he didn't realize that the theory claimed that observation in and of itself, without any physical disturbance, can instantaneously affect a remote physical system. So anyone else in their right mind wouldn't come to this conclusion. But Bohr was like, oh my gosh, no, you didn't prove things are real. You proved that things can instantly talk to each other. Like as soon as Alice measured it, instantaneously the other one became the same vertical polarization angle, you know. Bohr countered EPR with what he called a radical revision of our attitude as regards to physical reality. And here's an actual quote from him. And I just put it in here just so you know that not all physicists should ever write things down because, yeah. The criterion of physical reality proposed by Einstein, Podolsky, and Rosen contains an ambiguity as regards to the meaning of the expression without in any way disturbing the system. Of course, there is, in a case just like that considered, no question of a mechanical disturbance of the system under investigation during the last critical stage of the measurement procedure. But even at this stage, there is essentially the question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. Since these conditions constitute an inherent element of the description of any phenomenon to which the term physical reality can be properly attached, we see that the argument of the mentioned authors does not justify their conclusion that the quantum mechanical description is essentially incomplete. In English, he said, Bohr did not fault the logic of the EPR argument. He rejected their starting point, their condition for something being a physical reality. EPR's reality condition assumed that if two objects exert no physical force on each other, what happens to one cannot in any way disturb the other. So here these two waves are not just flying apart at the speed of light. They're flying apart at twice the speed of light. There's no way they can talk to each other. They're not putting forces on each other. They're not telephoning each other. There's no physical forces on each other. So let's be specific. Alice, by observing her photon, cannot exert a physical force on Bob's photon, which is moving away from her at, I should put, twice the speed of light. Therefore, according to EPR, she cannot have any effect on it. Bohr agreed that there could be no mechanical disturbance of Bob's photon by Alice's observation. So he agreed that nothing could physically happen. But he said, nevertheless, he maintained that even without a physical disturbance, Alice's remote observation instantaneously influenced what happens to Bob's photon. It's a very careful choice of words. According to Bohr, what constitutes a disturbance violating the EPR condition of reality? Only after Alice observed her photon to say it was polarized at 45.6 degrees was Bob's photons polarized at that same angle. So as soon as Alice looked, it influenced outside of reality, whatever, and it made the other one have that reality, have that angle. So how did Alice's observation affect Bob's photon? Can what is done at a distant place instantaneously cause something to happen here? Or strictly speaking, we should not say her observation affected Bob's photon or caused its behavior because no physical force was involved. Effects and causations are physical attributes, which Bohr said there was no physical attributes. That's why he used influence. Influence. Now, you could have come up with an explanation, but again, you can see how this can quickly go nowhere. Though Alice instantaneously influenced Bob's photon, she cannot communicate any information to Bob faster than the speed of light will allow. Bob always sees a series of random photon polarizations. Only when Alice and Bob come together and compare their results do they see that whenever she saw a photon polarized vertically, so did he. Whenever she saw a photon polarized horizontally, so did he. Is this all confusing? Yes. The fact of the matter is there is no way EPR and Bohr's response to it, which you read, can be correctly stated that does not either confuse or sound mystical. And Bohr was notorious for the way he spoke was like circular, like you didn't know what he was saying. Like he had to clarify. And when he clarified what he wrote, you need clarification on that. You're like, dude, what are you trying to say? Einstein rejected this response. He insisted that there is a real world out there, and the goal of science must be to explain nature, not just tell what we can say about nature. A photon displayed a particular polarization, Einstein claimed, because that photon actually had that polarization. He insisted that objects have physical properties independent of their observation. If any such properties, later called hidden variables, were not included in quantum theory, the theory was incomplete. Einstein derided Bohr's remote influence as being voodoo forces and spooky actions. So Einstein called it spooky action at a distance. Now we call it entanglement. And again, they come up with these words. It's like we have waves that aren't really waves. Now imagine the waves. I'm telling you not to imagine waves because they're not really waves. But if you were to imagine physically real waves, and they kind of cross each other and they're entangled like yarn, and they move away. So entangled means they're still connected somehow. So when you collapse one into reality, the other one, since they're connected outside of reality, connects. So you kind of get the terminology. To be clear, Bohr and Einstein would agree on the actual results of an EPR experiment, the Alice and Bob observations I described. They would just interpret those results differently. That's why no one actually did an EPR experiment. All physicists knew what the result would be. The Einstein-Bohr argument was regarded as merely philosophical. So entanglement is Einstein's spooky actions. That's what we call entanglement. Two particles can become entangled till the properties of one become directly connected to the other. Being connected, when one is measured, not only does it collapse into reality, but at that same instant, its entangled partner collapses into reality. Two entangled particles are connected outside of reality, so to speak. So in case it didn't make sense, I'm going to show you a video clip from that Nova special. It's the only part of the whole special I liked. And they explain the same thing, but with a bigger budget.
Lasers, transistors, the integrated circuit, the entire field of electronics.
If quantum mechanics suddenly went on strike, every single machine that we have in the US almost would stop functioning.
The equations of quantum mechanics will help engineers design microscopic switches that direct the flow of tiny electrons and control virtually every one of today's computers, digital cameras, and telephones.
All the devices that we live on, diodes, transistors, just that form the basis of information technology, the basis of daily life in all sorts of ways. They work. And why do they work? They work because of quantum mechanics.
I'm tempted to say that without quantum mechanics, we'd be back in the dark ages. I guess more accurately, without quantum mechanics, we'd be back in the 19th century. Steam engines, telegraph signals.
Quantum mechanics is the most successful theory that we physicists have ever discovered. And yet we're still arguing about what it means, what it tells us about the nature of reality.
In spite of all its triumphs, quantum mechanics remains deeply mysterious. It makes all this stuff run, but we still haven't answered basic questions raised by Albert Einstein all the way back in the 1920s and 30s. Questions involving probability and measurement, the act of observation. For Niels Bohr, measurement changes everything. He believed that before you measured or observed a particle, its characteristics were uncertain. For example, an electron in the double-slit experiment. Before the detector at the back pinpoints its location, it could be almost anywhere with a whole range of possibilities. Until the moment you observe it. And only at that moment will the location's uncertainty disappear. According to Bohr's approach to quantum mechanics, when you measure a particle, the act of measurement forces the particle to relinquish all of the possible places it could have been and select one definite location where you find it. The act of measurement is what forces the particle to make that choice. Niels Bohr accepted that the nature of reality was inherently fuzzy, but not Einstein. He believed in certainty, not just when something is measured or looked at, but all the time. As Einstein said, I like to think the moon is there even when I'm not looking at it.
That's what Einstein was so upset about. Do we really think the reality of the universe rests on whether or not we happen to open our eyes? That's just bizarre.
Einstein was convinced something was missing from quantum theory. Something that would describe all the detailed features of particles, like their locations, even when you were not looking at them. But at the time, few physicists shared his concern.
And Einstein just thought it was giving up on the job of the physicist. It wasn't bad physics per se, it just was totally incomplete.
That's Einstein's refrain. Quantum mechanics is not incorrect, insofar as it goes, but it's incomplete. It doesn't capture all the things that can be said or predicted with certainty.
Despite Einstein's arguments, Niels Bohr remained unmoved. When Einstein repeated that God does not play dice, Bohr responded, "Stop telling God what to do." But in 1935, Einstein thought he finally found the Achilles heel of quantum mechanics. Something so strange, so counter to all logical views of the universe, he thought it held the key to proving the theory was incomplete. It's called entanglement.
The most bizarre, the most absurd, the most crazy, the most ridiculous prediction that quantum mechanics makes is entanglement.
Entanglement is a theoretical prediction that comes from the equations of quantum mechanics. Two particles can become entangled if they're close together and their properties become linked. Remarkably, quantum mechanics says that even if you separated those particles, sending them in opposite directions, they could remain entangled, inextricably connected. To understand how profoundly weird this is, consider a property of electrons called spin. Unlike a spinning top, an electron spin, as with other quantum qualities, is generally completely fuzzy and uncertain until the moment you measure it. And when you do, you'll find it's either spinning clockwise or counterclockwise. It's kind of like this wheel. When it stops turning, it will randomly land on either red or blue. Now imagine a second wheel. If these two wheels behave like two entangled electrons, then every time one landed red, the other is guaranteed to land on blue. And vice versa. Now, since the wheels are not connected, that's suspicious enough. But the quantum mechanics embraced by Niels Bohr and his colleagues went even further, predicting that if one of the pair were far away, even on the moon, with no wires or transmitters connecting them, still, if you look at one and find red, the other is sure to be blue. In other words, if you measured a particle here, not only would you affect it, but your measurement would also affect its entangled partner, no matter how distant. For Einstein, that kind of weird long-range connection between spinning wheels or particles was so ludicrous, he called it spooky. Spooky action at a distance.
When you have one particle here and one particle there, and they are separated enough that there is no signal able to allow them to communicate, and they still seem to be talking to each other, then it's a big mystery.
What's surprising is that when you make a measurement of one particle, you affect the state of the other particle. You change its state.
There's no forces or pulleys or, telephone wires. There's nothing connecting those things, right? How could my choice to act here have anything to do with what happens over there?
So there's no way they can communicate with each other. So it is completely bizarre.
Einstein just could not accept that entanglement worked this way, convincing himself that only the math was weird, not reality. He agreed that entangled particles could exist, but he thought that there was a simpler explanation for why they were linked that did not involve a mysterious long-distance connection. Instead, he insisted that entangled particles were more like a pair of gloves. Imagine someone separates the two gloves, putting each in a case. Then that person delivers one of those cases to me, and sends the other case to Antarctica. Thanks. Before I look inside my case, I know that it has either a left hand or a right hand glove. And when I open my case, if I find a left hand glove, then at that instant, I know that case in Antarctica must contain a right hand glove, even though no one has looked inside. There is nothing mysterious about this. Obviously, by looking inside the case, I've not affected either glove. This case has always had a left-hand glove, and the one in Antarctica has always had a right-hand glove. That was said from the moment the gloves were separated and packed away. Now, Einstein thought that exactly the same idea applies to entangled particles. Whatever configuration the electrons are in must have been fully determined from the moment that they flew apart.
Einstein comes and says, look, if there is this strong correlation, it means that the direction of the spins were already determined before you do the measurement.
So, who was right? Bohr, who championed the equations that said that particles were like spinning wheels that could immediately link their random results even across great distances, or Einstein, who believed there was no spooky connection, but instead everything was decided well before you looked. Well, the big challenge in figuring out who's right, Bohr or Einstein, is that Einstein is saying a particle, say, has a definite spin before you measure it. How do you check that, you say to Einstein? He says, well, measure it, and you'll find the definite spin. Or we say, but it's the act of measurement that brought that spin to a definite state. No one knew how to resolve the problem. So the whole question came to be considered philosophy, not science. In 1955, Einstein died, still convinced that quantum mechanics offered, at best, an incomplete picture of reality.
All right. I stole a lot of their analogies. So, how do you prove this? Obviously, we have proven it. It's not just philosophical. And we come to the famous Bell's inequality. So for 30 years, by the time Einstein died, all the way to they were actually able to do these experiments, no experimental result could decide between Einstein's supposedly physically real hidden variables and Bohr's instantaneous influences. Moreover, physicists tacitly accepted a mathematical theorem claiming to prove that it was impossible for a theory that included hidden variables to reproduce the predictions of quantum theory. So there was a mathematician who came out with a theorem that nobody even tested. But the theorem basically said, if you were to prove that hidden variables, like what Einstein said, is true, then quantum theory would not just be incomplete, it would be wrong. Since everyone knew it wasn't wrong, they were like, well, Einstein, there is no hidden variables. This just is what it is. Even though later, I think like a college math professor actually worked it out and saw that the theorem was false, but his method of going about it. But that theorem undercut Einstein's argument for hidden variables. So because EPR's argument challenged none of the quantum theory's predictions, EPR did not confront the theory with an experimental challenge. Bell did challenge the theory. He derived an experimentally testable prediction that had to be true in any world that included an observation-independent reality and separability. Quantum theory denies such reality and separability. Bell's testable prediction was the straw man he created for experimentalists to try to knock down. Should Bell's straw man survive experimental challenge, quantum theory would be shown wrong. So Bell was able to actually take it out of the philosophical and create an experiment. Now this became the experiment, because if this experiment was proved wrong, then quantum mechanics would just fall apart and everybody would have to start back to base one. So here's Bell's theorem in a nutshell. All right? Suppose our world has physically real properties that are not created by our observation. That's what we determine as reality. So scientifically, physicists, when they say reality, they mean that things are real whether or not when you're not looking at them. So you're not looking at your phone is real. That's reality. Further, suppose that objects can be separated from each other so that what happens to one cannot simultaneously affect the other. That's called separability. Again, something we all know. I did the tennis balls, You take one tennis ball in San Francisco, one in China. We know if you knock the tennis ball down in San Francisco, there's no way it could have any bearing on the one in China. So we have separability. Quantum mechanics denies that, says no, nothing's separate. They're actually connected. From only these two premises, both assumed in classical physics but denied in quantum theory, Bell deduced that certain observable quantities could not be larger than certain other observable quantities. This experimentally testable conclusion of Bell's theorem, which must be true in any world with reality and separability, is Bell's inequality. So if Bell's inequality is shown to be false in any situation, one or both of the premises logically leading to it, meaning reality and separability, must be false. Therefore, if in our actual world Bell's inequality is ever violated, no objects with reality and separability can exist. So it's just setting it up. Philosophers and mystics have talked about reality and separability, or its opposite, universal connectedness, for millennia. Quantum mechanics puts these issues squarely in front of us, and Bell's theorem allows them for the first time to be tested. So any of you know about Zen Buddhism and the Asians, like they're, this grain of rice is connected to the lotus flower, like everything's connected. Well, that's kind of what we just said, like quantum entanglement, like who's to know how much entanglement is going on? So everything is actually universally connected somehow. So here's the experiment. So we're going to write, instead of drawing waves, we're going to draw them as like sticks. So this is 90 degrees, it's a stick going this way, 45 degrees, a stick going this way. And then you have the measurement device, right? And imagine the measurement device is like a hole. So anything at 90 degrees all the way to 85 degrees is going to go through, right? As soon as it gets too far at an angle, it's going to fall down. So you have a detector here, and you have a detector here. So you measure the ones, you know which ones go through, but you also know which ones don't go through. All right? So here's Alice and Bob again. And if they were to compare their measurements, they match up exactly. So Alice goes over here. Okay, 1. Okay, then 2. And then 1. And then 1. And then 2. Bob does the same thing. When they get together, they're going to match. Why? Because we already know this. They're twins, right? They're going to be the same no matter what. Here's what Bell said. Now let's take one, and you know what? Let's rotate it at some angle. We'll call it theta. Very small angle. So some photons now that would have gone through Alice's polarizer, had she not rotated, now go on her path too. So there's some that would have gone through, but now you rotate it just enough where it won't go through and it goes on path 2. Now Bob's is the same. So now when Alice and Bob match up, there's going to be some mismatches. Because obviously Alice is getting some on 1 and Bob's getting them at 2 because she rotated hers slightly. So let's say that she rotated hers to a slight angle where she has a mismatch rate of like 5%. So they do 100,000, and there's 5% of those are mismatched because that's how much they did in the rotation. By our separability assumption, Bob's photons are unaffected by Alice's polarizer rotation or by which path their twins took at Alice's polarizer. Alice and Bob coming together this time to separate their random data streams find some mismatches. Mismatches occur, for example, when some of Alice's photons, which would have gone in her path 1, had she not rotated her polarizers, went on path 2. But their twins at Bob's polarizer still went on path 1. So the percentage of mismatches would be small for a small theta. Let's say that Alice's theta was enough to change that it happened for 5% of her photons. Thus, she created a mismatch rate of 5%. All right, so everyone on board. Does this make sense? Okay. Part 2. Now, Bob is going to rotate his by the same angle. Now, he has to rotate it by the opposite angle. Because if he does them at the same angle, then it's the same thing as if he didn't rotate them at all. You know? So he rotates his, let's say 5 degrees. 5 degrees to the right. All right? So now they're going to have even more mismatches, right? So Alice, rotating her polarizer by theta, changes the behavior of her photons by the same amount as in the previous experiment. She changes what would have happened to 5% of her photons. The situation is symmetrical. Bob's polarizer rotation by theta changes the behavior of 5% of his photons in a different way, right, than what would have happened. What would have happened is what they would have measured if they didn't rotate at all. Since Alice and Bob each changed the behavior of 5% of their photons, and since every change should show up as a mismatch when their data streams are compared, we might expect a mismatch rate as high as 10%. And that's true. So if you go this way and 5% are off, if you go this way and 5% are off, in totality, we should have a maximum of 10% mismatch. Everyone buy that? Now I say expect because in reality, it's actually less than 10%. And the reasoning is simple. There's no way to get a greater mismatch rate in a statistically large sample. So there's no possible way that rotating one and getting a 5% rate and rotating the other one the same and getting a 5% rate, there's no way that overall you can have more than 10% mismatch rate. If it's true that these things are real and if they really are going when we're not moving and if they're really not connected outside of reality. We might, however, get a smaller mismatch rate. Here's how. It's likely that for some pairs of twin-state photons, both Alice and Bob each cause their twin to change its behavior. So the two photons of such twin-state pairs would thus behave identically. The data for such twin pair states would not be recorded as mismatches. So it's possible that there's ones that before both went on path 1, now that they're both rotated, they happen to fit and they go on path 2. Well, those won't be recorded as a mismatch. So that's why your data is always going to be 10% or less. All right? This should make sense logically because that's how it should happen in the real world. So So the mismatch rate they will see is likely less than 10%. In a statistically large sample, it cannot be greater. That's it. That's basically Bell's inequality. The mismatch rate when both polarizers are rotated by theta is equal to or less than twice the mismatch rate for the rotation of theta by a single polarizer. So the fact that you turn one 5 degrees and you turn another one 5 degrees, mathematically it's the same thing as taking one and turning it 10 degrees. It's a little bit, it's the same thing. Since space is the same in all directions, a rotation of one of the two polarizers in opposite directions by theta is equivalent to a rotation of only one by 2 theta. Thus, rotating a single polarizer in one experiment by theta and the second experiment by 2 theta can demonstrate the same inequality. So you can do the same thing by just taking one and moving it by 10 degrees or whatever. If you did 12.5, it'll be 25. Bell's inequality basically states that a rotation by 2 theta cannot produce more mismatches than twice those for a rotation by theta. Oh, and here's another second part of the clip. I figured I might as well. This is really funny how it happened.
In 1967, at Columbia University, Einstein's mission to challenge quantum mechanics was taken up by an unlikely recruit. John Clauser was on the verge of earning a PhD in astrophysics. The only thing standing in his way was his grade in quantum mechanics.
When I was still a graduate student, try as I might, I could not understand quantum mechanics.
Clauser was wondering if Einstein might be right when he made a life-altering discovery. It was an obscure paper by a little-known Irish physicist named John Bell. Amazingly, Bell seemed to have found a way to break the deadlock between Einstein and Bohr and show once and for all who was right about the universe.
I was convinced that the quantum mechanical view was probably wrong.
Reading the paper, Clauser saw that Bell had discovered how to tell if entangled particles were really communicating through spooky action, like matching spinning wheels, or if there was nothing spooky at all, and the particles were already set in their ways, like a pair of gloves. What's more, with some clever mathematics, Bell showed that if spooky action were not at work, then quantum mechanics wasn't merely incomplete, as Einstein thought. It was wrong.
I came to the conclusion that, my God, this is one of the most profound results I've ever seen.
Bell was a theorist, but his paper showed that the question could be decided if you could build a machine that created and compared many pairs of entangled particles.
Bell turned the question into an experimental question.
It wasn't just going to be about philosophy or trading pieces of paper.
And the experiment that he envisioned could be done.
You could really set up an actual experiment to force the issue.
Clauser set about constructing a machine that would finally settle the debate.
Now I was just a smug graduate student at the time. This really seemed like, wow. There's always the slim chance that you will find a result that will shake the world.
Clauser's machine could measure thousands of pairs of entangled particles and compare them in many different directions. As the results started coming in, Clauser was surprised and not happy.
I kept asking myself, what have I done wrong? What mistakes have I made in this?
Clauser repeated his experiments, and soon French physicist Alain Aspect developed some even more sophisticated tests, with one going to the heart of the Einstein-Bohr debate. In Aspect's test, the only way that measuring one of the particles could directly influence the other would be for a signal to travel between them faster than the speed of light, something Einstein himself had shown impossible. The only remaining explanation was spooky action. And so, a space experiment removed virtually all doubt.
Quantum mechanics is true even in the most mysterious and the most weird situation.
The results of these experiments are truly shocking. They prove that the math of quantum mechanics is right. Entanglement is real. Quantum particles can be linked across space. Measuring one thing can in fact instantly affect its distant partner, as if the space between them didn't even exist. The one thing that Einstein thought was impossible, spooky action at a distance, actually happens.
I was, again, very saddened that I had not overthrown quantum mechanics because I still had, and to this day, still have great difficulty in understanding it.
That is the most bizarre thing of quantum mechanics. It is impossible to even comprehend. Don't even ask me why. Don't ask me with regard to how it works, because it's an illegal question. All we can say is that is apparently the way the world ticks.
I love these MIT guys, you know. They're hilarious. So, quantum mechanics, if you work out the math, it comes out to 2 sine squared theta is greater than or equal to sine squared 2 theta. So if you do this for an angle of 22.5 degrees, or 2 theta is 45 degrees, quantum mechanics predicts that 0.3 will be greater than or equal to 0.5, which is exactly what they got. Now, of course, this proves that all this is true, that we don't have. Now, here's the tricky part. The mathematics doesn't say it invalidates both. It's either one or the other or both. Now, I maintain it's both. So it's either reality, meaning things are real even when you're not looking at them, or separability. Separability means things are connected outside reality. Overall, or it's both. Overall, quantum physicists usually probably like 75% side on just one, not both. And they choose reality as being true. So they say, you know, things really are real. Even though when you start talking about it, they're not really real, you know. But locality, separability, that's not real. Things really cannot be separated. They can be connected outside of reality, which is real. Yeah. Again, you just start going in circles. So we thus see that in the actual world, Bell's inequality can be strongly violated. And here's a quote from John Bell. In his arguments with Bohr, Einstein was wrong in all the details. Bohr understood the actual manipulation of quantum mechanics much better than Einstein. But still, in his philosophy of physics and his idea of what it's all about and what we are doing and should do, Einstein seems to be absolutely admirable. There's no doubt that he is, for me, the model of how one should think about physics. So the overall about quantum entanglement, it's real. So it's real. Yeah, okay. Now I'm going to show you, since we actually have enough time, another crazy experiment. And again, everything goes back to the double slit experiment, and we want to find other ways to see if we can trick, you know, because nobody ever wants to believe this really is happening. So before, I've got to go over one more property of light, and that's in circular polarized light. So remember, light comes in at all different angles. It goes through a polarizer, and it comes through at one angle. Well, you can have what's called a quarter wave plate, and that will actually take the light wave and spin it. And you can spin it either clockwise or counterclockwise. Now, I actually love this graphic because you see how much thicker this is?
Yeah.
And I talked to Duran about this. So when you watch 3D movies, this is what they use. They use quarter wave plates.
Yeah.
And so when you watch a 3D movie, they're actually flashing one image counterclockwise, one image clockwise, back and forth.
Yeah.
And since your eyes are polarized, you can only see one image in your right eye, then one image in your left eye. And they do that really fast, so fast, that's how you get 3D.
Yeah.
The problem with the real 3D effect is that it dims the movie so much, you know. That's why if you ever see a movie in 3D in IMAX, so much better, so much brighter, because they use a linear polarizer. Because they actually use 2 projectors, which, I don't know if you know, but those Harkins is all digital. Every one of those projectors is like $250,000. So if you have a 24 cinema multiplex, you multiply that out, and you have to double that. It's like, no. We're going to stick with the cheaper technology. So here's my point. So now we're going to do the double slit experiment, but we're going to use this new awesome tool, Entanglement. All right? So we're going to shoot a particle. This, it doesn't have a label. This is just a way they create, it's called a barium borate crystal. And when the particle hits it, it has this property, it's called spontaneous parametric down conversion. Basically, it's a very complicated thing on how they make entangled particles, all right? But let's just trust that they can take a particle, entangle it with another particle, and they can shoot it out 2 different directions, all right? So now we know what entanglement is, right? So we take a particle, we send the wave out, and now we send one this way and one this way. Now they're entangled, right? So if you observe one, you observe the other. If you don't observe one, you don't observe the other. They're connected. Now we're going to come to the double slit experiment, right? We're going to take one clockwise polarizer filter and put it over one slit. And we're going to take the other one counterclockwise and put it over the other one. So basically, we're observing which slit it went through. So when it hits the detector, right, if it has a clockwise polarization, which we can detect, then we know it came through the left slit. If it has a counterclockwise, we know it came through the right slit. So scientists just came up with another way to observe mark. Or in other ways, we know the which path information. So what happens with this entangled partner? If you look and you know which slit the particle went through, what do you get? The 2 lines, remember? Your entangled partner will do the same exact thing. It'll create 2 lines. Because if you collapse it here, as soon as you look at it, you collapse it, that collapses. It won't look like a wave. Of course, it's more difficult to see the wave when it's just a single thing, but you follow me. Now, we're going to do this. Now remember in that graphic, which let me just go back for a second. If you take a circular polarized and it goes this way as well, and you hit the quarter wave plate, you could turn it into a linear. It can go either direction. So you could take something and make it into linear. So whether this is coming through clockwise or counterclockwise, if it hits the wave plate this way, you can come out with any angle you want, 45 degrees, 90 degrees, whatever, all right? Why is that important? Is now we're going to put a polarizer. Now, see this dotted line? It's kind of hard to see. This happens at this moment in time. So let's spread this out and make it really big, all right? So this happens at 1 second. So 1 second, we observe it, right? And we all know what happens when you observe a particle. The wave collapses into a reality, becomes a particle, all right? This is later. So now they continue to travel. We've already collapsed the wave. Now we decide on its twin to put a polarizer. 45 degrees. As soon as we do that, what happens? Remember what happens? Whether it's going left or whether it's going right. If you put it through a 45-degree filter, it's going to come through at 45 degrees, right? So if it changes to 45 degrees, what happens is now you don't know which slit it went through. So if you don't know which slit it went through, it then should turn back into a wave. This is what's called the quantum eraser experiment. So, and the reason why is because we erased what we just did. So we observed the path the particle took, we marked it, we collapsed it into reality, and then later we erased it. So even if you imagine the waves congealing into a particle, now how do you imagine that particle then you decide later on its twin to be like, you know what, I looked where you're going to go, but now I'm going to unlook. I'm going to erase it. And then that particle turns back into a wave. And you can do this over and over. You could do back and forth. It doesn't matter what you do. You will always get the correct results. So you're literally erasing the results. So now it gets even more complex. And again, they were hoping to maybe see a different result. Like maybe we can trick it. Maybe we can find out really what path it went through. It didn't matter. And that led to the ultimate of all experiments. This was finally perfected in 2007. So this is pretty modern. This is what's called the delayed choice quantum eraser experiment. And it goes like this. Once again, we have the light, double slit experiment. So it can either come through the top or the bottom slit. All right, top is red, bottom is blue. It's going to hit the barium borate crystal. That's what's going to come through. It's going to create an entanglement and shoot it two different ways. Well, it uses what's called a Gland-Thompson prism. And a prism takes a wave of light and splits it and reflects that wave of light, splitting it in half, two different directions. So the whole point of this is, if it comes through one hole, doesn't matter which hole it comes through, we're going to entangle it, and then we're going to reflect those two entangled partners different directions. All right? The first direction is going to go up, it's going to reflect through a lens, and it's going to hit a sensor. All right? Its entangled partner is going to hit a prism. They have a prism here just to bounce. They're trying to control this. It's going to bounce off a beam splitter. So this green thing is a beam splitter. Remember, it's just like a silver mirror. So it has a 50% chance of bouncing off or going through. So if it bounces off, it's going to hit this detector here. You got another detector. If it doesn't bounce off, it's going to go straight through. It's going to bounce off a mirror. So that dark gray is a mirror. All right? Bounce off, hit another beam splitter, and it either can go through or bounce off. If it does bounce off, it's going to hit this detector. If it doesn't, it's going to go through and hit this sensor. So here we trace out all the possible paths. The top one is only going to go to that top detector, all right? The bottom one could either bounce off and register there, or the photon can go through, bounce off the mirror, and either bounce off and go there, or go through and go there. Everyone follow me?
Yeah.
So it looks kind of complicated, but if you break it down, it's not. And then you do the same thing with the bottom half. And I made it dark blue so it's easier to see. So same thing. It goes up to the top, or it's going to go down and it's going to bounce off and go there, or it's going to go through, hit the mirror, either go through, have 50-50 chance, or bounce off and go to this detector. So this is the experiment. So again, broke it down, looks kind of complex. So now let's zoom in. So remember, this detector at the very top, when we detect something, what do we know? We know that it could have either been the top slit or the bottom slit. Because either way, one of these is going to go. So if we don't know which slit it came through, what should we see? We should see an interference pattern. Now I use this graphic because it's just easier, you know, just the graded lines, it means interference, all right? So that's going to be interference. Same thing with the other ones. D2, both the lines go there. So if we register something there, we don't know which one it went through because either of them could have gone there. That's going to be interference. Now D4, if that registers anything, it had to come through the top slit. So we know which path it went through. Thus, we observed which slit it went through. So that's going to have a clump pattern. So I just put the two lines. So everyone get those graphics?
Yeah.
Make it simple? Okay. And then we'll do the same thing with the rest. So this guy down here, oh, it's going to be two lines because it's just blue. And this guy here is going to be interference. All right. Everyone follow me so far? Okay. Here's the caveat. Remember, whatever happens to the entangled partner happens to the other one. So this top guy up here isn't really an interference. It registers whatever its partner does. So if its entangled partner, boom, gets observed, it's going to what? Collapse into reality, right? So that one's going to show a line. It's going to collapse into reality. If it goes and it bounces and it's here, and we don't observe it, then we didn't collapse into reality, and it's going to behave like a wave. And up there, it's going to register like a wave. So this one's called 0, and this is 1, 2, 3, 4, whatever. 0 is going to match its pair. So whatever these bottom four are, the top one is going to match it. Everyone get that? Does it make sense, Ron? Don't fall asleep on me.
No.
All right. Now, I made this like 2 years ago, this graphic, and that's when they had a different, the prism was not a square, it was a triangle, so you know. I'm going to, remember, this isn't to scale. I'm going to show you an animation of the actual path it takes. And this is not to scale, but it's correct in its assumptions. Now I'm paused. Anyone see the problem here? Let me go back. Remember what I said about that top one? So what's the problem?
It's already reached the sensor.
Huh?
It's already reached the sensor.
Yes.
At the top.
I told you that that top one shows the exact results that you get on whichever bottom sensor gets. But you can see, no matter what you do, the top sensor is going to be read before the bottom sensors. So let's put it in our graphics. Let's say, for example, that we are going to observe the particle is going to come through the top slit, and it's going to bounce off and register there. That means that top one is going to give us the 2 lines. But as you can see, the problem is I'm going to see the 2 lines before it actually hits and registers. If we do if we do this one, it's even a bigger deal because then it's a lot further pattern. So we're looking, I register an interference pattern. Light still hasn't even reached the sensor. So now we are seeing into the future. This will always give you the result of what these bottom 4 are. But you will see the result before you get it. So now let's imagine we're at a computer, right? And let's imagine these are spaced out across the whole, from here to the moon, all right? So we're looking, and we make a measurement. Boom. All right, we see an interference pattern. It's on our screen. I'm looking at an interference pattern, all right? But obviously, its entangled partner, it hasn't even made the random decision on where to go. Let's say it makes the random decision to go there. Now, if it goes there, it's not an interference pattern. It's a clump pattern because it got observed. I know which slit it went through. So then what happens to me? Does it just go poof and then change into a double line? Does my brain get erased? Do I even remember seeing it? Like what happens if you go back and change the past history to something you saw? That's not even a real question. It's just kind of funny. So you can see how crazy this is because now they were trying to prove retrocausality, that what you do changes the past, but now we're basically looking into the future. But are we? So remember, this is an eraser experiment, but the eraser is kind of hard to see. So if you take it here, if you take an object and split it out 2 ways, 50-50, and you have the mirrors, and you put a detector up there on the blue and on the red, you know which way it went, right? Just like here, it bounces off one beam splitter, then it bounces off a mirror. But if you go ahead and put another beam splitter, then you erase that information. Because you did know where, like, oh, this went to the left. It went to the left. It went to the, oh, now it's mixed again. You don't know whether it went left or right. All right? So that's where the eraser comes from. But, in addition, see the waves? Because of the beam splitters and just the way the experiment's designed, these 2 wave functions are like offset. And it's written out here. You see it's lambda plus 2k, because you have lambda plus k, this is lambda plus k, and lambda plus lambda. So you end up getting lambda plus 2k. And the other one's lambda over 2 plus 2k. So it comes out to that little picture graphic you see there. Why is that important? What's important is the counters. So counter 0 was the one at the very top. So if 1 gets interference, 0 sees interference. If 2 gets interference, 0 reads interference. Lines, 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 lines. But here's the problem. These 4 are, each time it's hitting one of these 4 randomly, right? But 0 is just one counter. So as you can imagine, it's going to fill up, if you take all of these and overlap them, it's just going to fill up with gibberish. You know, it's kind of like playing 2 different movies like on top of each other, and it's just going to be a mesh of light. So how do you determine actually what was there? Well, remember, they're all connected to the computer, which is the coincidence counter. So every time you send a pair, yes, this one registers first, a nanosecond before this one. But you know for every tick here, you know what tick that one came. So the reality is, the way the experiment's set up is you can't see the future. Remember, you don't see an interference pattern. Remember? You have to have thousands of these little dots appear, and over time, you see an interference pattern. You don't see two slits right away. Thousands of them have to go through, and then you see two slits. So if you take thousands, millions of these between the four of them, by the time you have enough information to determine whether it's interference or whatever, it's all blurred. It's all just a mesh. After the fact, you can extract it. So let's say we do 100,000 measurements, right? And we have two, clear experiment. We say, hey, computer, for every time something hit 2, pull out the 1 from 0. And what the computer will pull out is an interference pattern. Double slit. Hey, for every time something hit 4, show me the coincidence, the corresponding pair. So even though the book was being written, you could not read the book until it was done. Then you have to come together and actually talk and be like, hey, what did you get when I got this? Does that make sense? Yeah. So it's kind of like, I don't know, the only thing I can think of in this is like the book of Daniel. You know, or like the one of the books. I was like, how are these books written? And why can't we just read them, you know? And here you have a book being written. It's all written. But you can't decode it until it's the right time. And you could stop and go back and compare the notes. Now, this is huge because you're tempted to say, like, well, design a better experiment. Like, make it so the waves aren't offset. They've done it. They tried all different ways. No matter what you do, the same type of effect occurs, where you cannot read the data up top until after it's over. So there's no way to see into the future. That's why I said quantum mechanics in the mathematics, it forbids looking into the future. Unless you set up a way where you can't change it. And obviously, if you're looking after the fact, you can't change it. Now, this experiment, we'll talk about it next week. If you take this and now stretch it out all the way to, like, let's say the sun. The sun's a couple 100,000 miles away. So this is us, and this is the experiment hitting the sun, entangled. Now you can see how we can see a solar flare from the sun instantaneously. We're seeing into the future. Because in that experiment, when you go that far away, you can't change the outcome. You know, the sun is 8 light minutes away. There's no way you can change the outcome of that light coming at you. But you can actually predict what is coming at you. But here you just see another way. Every time they try entanglement, whatever, to try to disprove that, you see over and over, this is true. So it makes more sense that you're going back, and whether you're going back to create your past history, whether you try to record your history forward, you can never look forward to when you could change it. Any questions? I know that's a lot to absorb, you know. And it's 9 o'clock. So I guess I'll stop. I was hoping to get to teleportation, but next week we'll go over teleportation and spin. You're going to hear about spin all the time, and I didn't really talk about it. You know, they'll spin up, spin down, they show. We're going to talk about spin. So yes, John.
So when it hits the 0 plate, because they're entangled, when it's a 0 plate with either as, say, a particle or a wave, does that then change which other plate that it hits? Because once it hits the 0 plate, it's already, like you said, it's already there with that information, particle or wave.
Well, we
so
don't.
it would basically, the result would effectively create the experiment.
The result that you're getting up top.
The result up top would basically create the experiment at the bottom.
Well, that goes all back. That's why I spent that time earlier. It's all two sides of the coin. Remember with the box pairs? It's either your perspective, that what you did created the outcome, or it could be that the outcome already existed and that you looked ahead to see it. Either way, we don't know because we can't see, even though we measure it, we can't see what it looks like in the big picture until it's too late, until after the fact. Does that make sense? Because if this hits this guy, right, that means it's going to form two lines. But it's going to form two lines over what? A period of time, over thousands of dots. You just see one dot. Like, you don't know whether you're looking at an interference or you don't know if you're looking at particle. You don't know until you get thousands and thousands and thousands. And at that time, the thousands and thousands have been distributed between all your different ways. So by the time you get enough data to form any pattern, this one is going to look like a solid block of just mess. You will have no pattern. Because if this is a combination of all of these. So if you take all of these and put them on top of each other, and you can't tell here, but because of the lambda, because of this, they're slightly offset. So I don't know if you could tell. See, this is a little bit offset. Yeah. They don't exactly line up. And that was the last thing I was going to do, because you know me, I'm a perfectionist. I was going to take them all and lay them on top of each other and show you how it turns solid red, but I didn't have time. But you put them all up. But again, a lot of guys were like, oh, well, we just need a better experiment. It's always like, oh, it's a better experiment. Let's try it a different way. Doesn't matter what you try, you cannot do that, because if you could achieve this, then you could look into the future. And mathematically, you cannot predict the future. It's unpredictable. It's random. But even though you can record the future, you can only record and see the future if you cannot change the outcome. That's why I mentioned the quantum telescope. Or the government wants to perfect quantum radar. You know, it's like, look, we can see Iran launch nukes. But we can only see it if we have to design the experiment in a way where we cannot change the outcome. I don't know if that's possible. Unless you tie everyone's hands around their back and they turn off all the phones. We can watch them nuke us, as long as nobody in the room can say anything. As long as you can do nothing to stop it. And of course, quantum knows everything. Whatever you do, whatever decision, so whether that's predetermined by what you did, or what you did changes your predetermination, it just gets weird with it. And that's why next, again, you use this ability to now go into teleportation. That's quantum entanglement, you know. And the spin is just kind of silly. But the way the spin works, just so you know, every particle will either spins up or spins down. All right? It gets more complex than that. The funny thing about that is that's where you get the universe is digital. Again, you go to Barnes & Noble, because what is digital? What all computers understand is what? Ones and zeros. Right. Everything is inherently up or down. Or it's actually called half spin and a negative half spin. You know? And just so you know, it's a half spin is a full spin. So spinning around half is one full rotation. So in order to make a full rotation, you have to spin around twice. Right. Again, it's just kind of hurt your head, but let this absorb, and then next week, if you let it soak in, you know, try to watch the video on your smart Galaxy phones, you know, your tablets, and that's it, unless you have more questions. No? You good? All right. Let me stop my recording. Manny, I got